Okay, so now we're going to talk about the ionic solids. So, ionic compounds, most of them have crystalline structures. And they're related to the unit cells we looked at, but instead of all of the spheres being the same, we now have at least two different kinds of spheres. We have to have a cation and an anion. So when we talk about the coordination number, we're looking at the number of cation-anion interactions. Those are the interactions that lower the potential energy, that cause it to come together. So generally, if the cation and anion are close in size, if they're similar in size, you can get a higher coordination number, and so that's going to have a lower energy. So in these crystal structures for ionic solids, they're balancing the coordination number. We have to consider charge neutrality and different ion sizes. So if the ions have similar sizes, such as cesium chloride, cesium chloride is going to have chloride ions at the lattice points of a simple cubic unit cell, and then one cesium ion will be in the center of that. This is a simple cubic unit cell. It's not a body-centered cubic unit cell, because this is a different particle. So you look at one of the ions, and that determines what the unit cell is.
Now the ion is still in its form, right? When they're combining together?
Yes. So you can think of an ion as a marble with a charge on it. Okay. And here's another marble with an opposite charge, and so they're going to be attracted to each other like magnets.
The molecules are the ones that are...
Molecules are the ones where we talked about the overlapping orbitals, and they sort of mush together and become one blobby thing. Yeah. So if we look at this cubic unit cell, we've got an eighth of each we have 8/8 of chloride ions, right? So one chloride ion and this cesium ion in the middle. And the charges are +1 and -1, and so you have to have one of each in order for the charge to be neutral. So that limits what sort of a structure you could make out of these. If ion size was the only consideration, here we've got different ion sizes with sodium chloride. The sodium ions are much smaller. If ion size was the only consideration, we could fit a lot of sodium ions around the chloride ions. You've got some like oranges, and then you're going to stick some blueberries in the box. And the blueberries could just trickle in and fill up a lot of those spaces. But you have to have one chloride ion for every sodium ion. You can't have a whole bunch of extra sodium ions, because then it won't be neutral. You have to have charge neutral.
With these, when they're in a solution, they're grouped up. Just you can have one sodium and one chloride.
In a solution, the sodium ions and the chloride ions actually separate from each other, and each is surrounded by water molecules with the ion dipole forces. Yeah. So we have to have a 1-to-1 ratio. So this ends up having the structure, it's also called a rock salt structure, where the chloride ions are occupying a face-centered cubic. So here we've got the corners and one chloride on the face. And then the sodium ions occupy the spaces in between. So in this unit cell, we've got 4 chloride ions and 4 sodium ions. If we have an even larger difference in size, now the coordination number is going to get even smaller. So zinc sulfide can arrange itself in a structure called zinc blend. And here what we have is sulfide ions in a face-centered cubic structure, with zinc ions in 4 of the 8 tetrahedral holes. What the heck is a tetrahedral hole? Well, if you have these four spheres forming a tetrahedron, the hole between them is a tetrahedral hole. This is very hard to visualize. So here's a zinc ion, and they're showing these sticks. That's showing the ones that are around it in the tetrahedron. We also have some tetrahedral holes that don't have zinc ions in them. There are actually 8 tetrahedral holes, but they're not all occupied by zinc because we have to have an equal number of zinc and sulfide ions. So this is face-centered cubic, and so it also has 4 of each ion. Then when you get different charges, you have different numbers of each kind of ion, and then things get even more interesting. So here we have a 1:2 cation to anion ratio, like calcium fluoride. There's 1 cation and 2 fluoride ions. So this one with calcium fluoride is called the fluorite structure. The calcium ions are in a face-centered cubic. So here's calcium, 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 calcium. So that's one of the faces, and this is in the center. And now we need twice as many fluorides as chlorines, and so the fluoride ions can occupy all 8 of the tetrahedral holes. If you have something where you have, like maybe sodium sulfide, where you've got 2 cations to 1 anion, then that might take on what's known as the anti-fluorite structure. It's anti-fluorite because the charges, the cations are in the opposite places. Okay, so which compound is most likely to crystallize in the zinc blend structure? And they're giving us formulas of 3 ionic compounds, and then they're giving us the radii of the ions. So let's go back and look at the zinc blend structure and see what we learned about it. The title here is Ionic Solids with Large Size Differences. So the size difference between the ions is big. That's a characteristic of the zinc blend structure. And what's the ratio of cation to anion here? It's 1:1. So zinc sulfide, there's 1 zinc and 1 sulfur. In the unit cell, you've got 4 zinc and 4 sulfur. Okay?
So a zinc blend structure doesn't necessarily have zinc in it.
No. It's named after a mineral called zinc blend that takes on this structure, but then it was observed that other substances also take on the same structure, but they may be completely different compounds. Like the rock salt structure doesn't have to be rock salt. It could be another type of ionic compound, could also take on that structure. So here, in trying to identify which would be most likely to be zinc blend, what we're looking for is equal numbers of ions and large size difference. Oops. So someone says B is gone. Yes, that's correct, because here we don't have an equal number of ions. So that's going to most likely be the fluoride structure, but that's not what this question is asking. So now we've narrowed it down to these 2 choices, rubidium chloride and copper iodide. So we're going to look here, we've got 96 and 216. Here we've got 148 and 181. Which one has the larger difference? Letter C. So this is the one that's going to be, of these 3, the most likely to crystallize in that structure. Yes?
So it is right, like with the radius of non-metal is larger than the
Well, here when a metal forms an ion, it becomes much smaller than the metal atom was. I guess I'm not sure exactly what you're asking. Mm-hmm.
So the metal is larger than radius on the non-metal. Is it more crystalline or?
Well, sometimes the metal's larger and sometimes it's smaller. Yeah.
But both they have crystalline.
Well, they will all form solids, but exactly how they arrange themselves is going to depend partly on the relative sizes. So if the cation and the anion are approximately the same size, they'll form one kind of structure. If they're moderately different, they'll form another, and if they're super different, then they'll form another. And we're only looking at a few of them. It's actually much more complicated.
So is there like a standard for when it goes for the size difference? Like if the size difference is over 100 picometers?
No, there's no dividing line. What we're talking about right now, these are just sort of generalizations, just to kind of give you an idea of why does this compound have this structure and this other one has this structure. And some of these, probably many of these, you can get to crystallize in other forms under certain circumstances, but they're going to have a preferred crystalline structure. You look at this rock salt structure, and this is definitely a cubic unit cell. Have you ever looked at salt grains? Are they?
Tiny cubes.
They're little tiny cubes, right? This is why. It's because of how the ions arrange themselves to have the lowest potential energy. Other things will make, the monoclinic crystals and all these other crazy shapes because of the relative sizes and charges of their ions. There's a whole branch of science studying stuff like this. And a lot of this class we're telling you a little bit about this and a little bit about that and a little bit about the other thing.